Hi everybody, welcome back. We're going to talk a little bit today about solubility products, right? So, as you guys all know by now, in general, when we put a salt in some water, we're going to get some dissolution, right? A good example of that would be, for instance, when we take silver chloride, right? So AgCl. You could also do this with sodium chloride, NaCl, or any other salts in existence, right? If we took that solid, as we so often do, and we dumped it in some water, right? What would happen is that some of that would dissolve in the water, and it would dissolve into two ions essentially, right? So you would get your silver ion in an aqueous solution, because remember we dumped it in water, and you would get a chloride anion, again in an aqueous solution, because you just dumped it in some water, right? Now that's not necessarily to say that the minute that you put your silver chloride in the water, it's all going to instantly dissolve. And that's certainly not to say that if you kept dumping it in and dumping it in, it would always keep dissolving, right? At some point, as we know, a solution becomes saturated, right? And just to remind you, essentially what that means, right? When we say something is saturated, we mean that it's at equilibrium between the solute and its ions. And again, just to be clear, because I know this is a lot of jargony type terminology, right? This over here is the solute. The solvent, in this case, is water. That's what we're dissolving it in. And over here, we have the ions. So essentially all we're saying is once we've reached equilibrium, we've reached the point at which, if we put any more in, it's just going to spit out more solute, right? Because we have reached the absolute maximum of what can dissolve in the water. So hopefully that makes some semblance of sense, right? So now to apply that to what we've already kind of learned and talked about together in here. We've been talking a lot recently about equilibrium constants, right? Equilibrium constants. So you might remember our old friend, big K, right? And what we're going to be talking about in this particular video is the solubility product constant. So that's just annotated KSP. So again, that's the solubility product constant. And essentially what this is, right, all this is describing is the extent to which a salt can be dissolved in water, in H2O. Right? So this is usually an experimentally found value that you can look up online or whatever, right? And again, all it is essentially just somebody kept dumping silver chloride or whatever into water and dumping it in until they found that exact tipping point where the solution became concentrated and where we sort of reached our saturated point, at which the solute and the ions were in perfect equilibrium, right? So let's take a look at a couple of different examples of this, right? And let's use the example we've already got going above, just because that's easy, right? Of silver chloride, right? So we already know that for any equilibrium constant, right? Essentially what we're looking at is the concentration of the products over the concentration of the reactants. And we also know that, for instance, if there had been any sort of coefficient, like if this had been 2Ag, we would have said Ag squared, right? The one kind of wrinkle here is that when we're dealing with this particular constant, when we're dealing with solubility, we're inherently dealing with something that's solid. And when we're talking about K, we don't necessarily care about our solid compounds or how much of our solid compounds we have because, guess what? They're solid, so they're not really going to affect concentration or equilibrium the way that liquids and gases will interact with each other. So hence, instead of looking at just straight up K, we've developed KSP, which essentially just disregards this fellow down here and just looks at the things that are dissolved, which makes sense since, again, we're looking at specifically solubility. We don't care about the things that aren't soluble, right? So I happen to know, because I looked it up on the internets, right, that silver chloride has a solubility product constant of, drumroll please, 1.7 times 10 to the negative 10th power, and this is at specifically 25 degrees Celsius. And just so you know, these constants will always be in terms of 25 degrees Celsius. That's, so if you see that at some other temperature, you want to be careful, right? Because remember, solubility changes as temperature changes. That's one of the first experiments we do in class, right? Is looking at what happens to the solubility of salt as we increase the heat of water. So watch out for that. We're talking about solubility constants specifically at 25 degrees Celsius. Okay, so that all kind of gives you a starting place here. Let's try a couple of, let's try just a quick sort of brain teaser type question here. Let's say that I gave you all this information. I said, I would really like to know what the molar solubility of silver chloride is. And again, molar solubility essentially is just referring to how many moles per liter of solute can I dissolve? I ask. Well, guess what? I can find that using my solubility constant, right? Essentially, all I have to do is I have to think about my original equation, right? So how many moles of silver chloride do I have? That's right, 1. How do I know? Because it's just silver chloride. I don't have a 2 in front of it. I don't have a 3 in front of it. It's just 1 silver chloride. So I've got 1 mole of that, right? But, it could be, we can treat it as like X moles. Because remember, that doesn't necessarily have to be a mole. It could also be like 1 molecule that we're talking about. So over here, again, we have correspondingly 1 mole of silver cations dissolved in aqueous solution and 1 mole of chloride ions dissolved in aqueous solution, right? So we have over here on this side of the equation, where this over here was just x, you get x plus x, right? So in other words, if I were going to plug those quantities in over here, you'd essentially be saying KSP equals x times x, or consolidated, x squared equals 1.7 times 10 to the negative 10th, right? And then from there, we're just going to want to do a little basic calculation. Here, I'm going to do this in. Oh, I think I'm going to do it in brown. Nice brown color. Right? So that's essentially just going to be x is the square root of 1.7 times 10 to the negative 10, right? Which ends up being, when you guesstimate it, just about, 1 and some change. Call it, I don't know, like 1.3 times 10 to the negative 5. So essentially what that means is that 1.3 times 10 to the negative 5 moles can be dissolved per liter of solvent for AgCl. Okay. So now we're going to try another practice problem. This is, I believe, an MCAT practice problem, if you're paying attention to that sort of thing as we go along together. Okay, so the value of the solubility product for copper 1 chloride is KSP equals 1.2 times 10 to the negative 6th. Under normal conditions, so again, just meaning like temperatures about what it should be and all of that, pressures what it should be, the maximum concentration of an aqueous copper chloride solution will be. Okay, so remember, essentially all they're saying here, right, is that you're taking some copper 1 chloride, right, and you're dumping it in some water, and you're looking to see what dissolves, right? And what ends up happening is that you have some copper that pops off from chloride. And now you have a copper cation and a chloride anion, right? And these are all, again, in aqueous solution. Aqueous solution. These are in water, right? So if we were looking at our solubility constant, again, we know that we're just looking at the concentration of these ions. So Cu times the concentration of Cl, like so, right? And they've told us that all of that is equal to 1.2 times 10 to the negative 6th. Okay, now remember the logic that we used earlier? I know it might still be a little iffy in your minds, right? But essentially we're saying, okay, so we start over here. If we assume that this is like quantity X, right? And you could think of this as like 1 mole, right? Well, over here you have another 1 mole. Essentially you have that same quantity X, and you have yet another mole, that same quantity X, right? So then you would just plug that right back in over here. X times x, right? Which we know is the same as saying x squared. And we know that's all equal to 1.2 times 10 to the negative 6. So at this point, all we got to do is solve for x, right? So if we do the square root, we will find that again, 1.2, I mean, that's going to stay roughly the same. The square root of that is not going to change drastically. The square root of this guy, you're simply going to take half of your original. So in the case of even numbers anyway, so 10 to the negative third. So then if we're looking at our multiple choice problem over here, they're asking you, what would the maximum concentration be? Okay, well, we know it's this, right? So we're essentially just looking for the one that matches, less than 10 to the negative 6. Well, no, because 10 to the negative third is much greater than that. Still greater than 10 to the negative 4, so we can get rid of b. Oh, yeah, no, this makes sense. It's greater than negative 4, but less than negative 2. So negative 3 would fit that profile. Beautiful. Okay, moving right along. Here's another. The solubility product for lithium phosphate, that's Li3PO4, is KSP equals 2.7 times 10 to the negative 9. How many moles of the salt would be required to form a saturated 1 liter aqueous solution? Hey, by the way, as we're going through these, it occurs to me, just in case it hadn't already occurred to you, I thought I would remind you that because this is a recording, you can always pause and try to work out the problem yourself and then hit play and listen to the rest of the recording to make sure you've done it properly. I just don't want you guys to feel like you have to spend this whole time just sitting here passively listening. You can absolutely be attempting to work these out on your own before I do the explanation. Oops, sorry about that. Okay, so I'm going to assume that if you wanted to pause, you would have paused here, right? And that the rest of you who are still listening want the explanation. So here we go. So again, we know that essentially what happened here is we had some lithium phosphate that was solid that got dumped into some water, right? And now it's in equilibrium, right? So essentially what this means is that the lithium and the phosphate have sort of broken apart from each other, right? Well, the phosphate is all going to be one happy little cation with a -3 charge, right? But now you actually have 3 positive lithium ions floating around, because remember, we needed 3 of the lithium in order to balance out the charge of this guy, of the phosphate, right? So that's going to change the equation up a little bit, because we know that whenever we have a coefficient in front, we're going to have concentration of lithium to the third power times concentration of phosphate anions, right? And we're going to do pretty much the same thing we did before. Again, the logic is, largely the same here. You're going to say to yourself, okay, well, over here, let's say I have X mole. Well, here I have 3X, and over here I have X. So now I just have to plug those back into my solubility equation. So solubility constant is equal to 3X, remember that's my concentration for lithium, 3X cubed times X. Okay, so from here we're going to simplify. So, the one thing I'd say is watch out, guys. Remember, 3x cubed is not going to be the simplification here. It's going to be 3 cubed times x cubed. So 3 cubed, you might recall, that's right, 27. And then we've got x cubed, and that's all times x. So that simplified is going to give me 27x to the 4th power. Phew! Okay, and then and only then can I set all of that equal to my solubility constant, which they gave me up here. 2.7 times 10 is -9th, like that. Okay, and then I just have to solve for x. So again, if you feel like it, do a quick pause here, see if you can solve for x, and then I will confirm for you. Okay, so if you found that x should equal 3.2 times 10 to the negative third or thereabouts, you're doing awesome. Congratulations. Okay, so let's try just a couple more problems here. So this one's kind of a fun reversal of some of the problems that we've already done. By experimentation, it is found that a saturated solution of barium sulfate, right, um, at 25 degrees Celsius contains 3.9 times 10 to the negative 5 moles per liter of barium ions. Find the solubility product constant of this salt. And again, because of the nature of this word editor, I apologize, unless I'm copying and pasting from another document. Some of my formatting is a little weird. So again, this is SO4 is how you would normally see this. And Ba2 plus is how you would normally see this. And then KSP is how you normally see this. It's really hard to do subs and super annotation in this particular editor. Okay, so essentially, as usual, we're going to start by kind of trying to visualize what the actual reaction would look like. So you dump some barium sulfate into some water, right? Some unsuspecting water, right? And you would get some barium cations popping off and some sulfate anions popping off, like so. Okay, so we know that they've told us that this specifically, the barium specifically, is at this concentration. Times 10 to the negative fifth. Well, remember our logic from earlier. We said, okay, so where this is x, or equivalent to 1 mole, this is also equivalent to 1 mole, and this is also equivalent to 1 mole, right? So if this is 3.9 times 10 to the negative 5, right, then so should this be, and so should this be, right? Hopefully that makes sense. So again, if we just set up our solubility constant, we know that that would be equal to the concentration of my barium times the concentration of my sulfate. And we also happen to know both of those concentrations, right? We know that they are both 3.9 times 10 to the negative 5. Woohoo! Fantastic. So then all we got to do is a little basic math, right? So what we end up with is roughly 1.5 times 10 to the negative ninth. Awesome sauce. Well done. Okay. Let's try one more. Okay, so just to warn you, I feel like this is probably the hardest problem in this set, so prepare yourselves, okay? Suppose we have two solutions. One solution contains 1 times 10 to the negative 3 moles of silver nitrate per liter, and the other solution contains 1 times 10 to the negative 2 moles of sodium chloride per liter. So if we combine 1 liter of each solution and we mix them together to form a 2-liter solution, they want to know, will a precipitate of silver chloride form? And remember, precipitate is just like any solid that literally drops out of the solution. Again, if we have a solution that's super saturated of salt at a high temperature in water, you guys have probably noticed this phenomenon. If you lower the temperature of the water, some of the salt is going to precipitate out because the solution is no longer hot enough, to handle all of that solution or all of that solute, right? So they're essentially just saying, like, when we mix all this stuff together, are we going to get a precipitate? Believe it or not, we actually have enough information to calculate that. So let's do that together. All right, so first off, silver nitrate, right, is going to dissolve in an aqueous solution to form Ag and NO3. Obvious enough. All right, hopefully anyway. NaCl, as we know well, dissociates into sodium and a chloride ion, like so. Right? So in the original solution, in the original concentration, right, they told us that we had 1 times 10 to the negative third mole of this guy, which means, you guessed it, we also have that much of this guy and that much of this guy. They told us we had 1 times 10 to the negative 2 mole of my sodium chloride, which again means that there's that much concentration of sodium ions and that there's that level of concentration of chloride ions, right? So that means that we know already all of those concentrations, right? Now here's the tricky bit. This is the bit that might not be the most intuitive in the world. These concentrations, remember, are for 1 liter. 1 liter of water each. Right? But remember, we're dumping them both together. So now they're all in one giant 2-liter bucket, if you will, right? And that means that the overall concentration is going to change. The overall concentration is going to get cut in half, right? It's going to get cut in half because suddenly you no longer are talking about this many moles per 1 liter of solution. You're talking about this many moles per 2 liters of solution, right? So now we're talking about essentially, again, half of this. So 1 becomes 0.5 times 10 to the negative third moles. If it makes you feel better, you can rewrite this as 5 times 10 to the negative 4 moles. You can essentially just move the decimal place over by 1, right? And then you're going to do the same thing over here because this concentration is also getting halved. So it's going from 1 to 0.5 times 10 to the negative 2, or 5 times 10 to the negative 3 moles. Okay, so hopefully I haven't lost you yet. Hopefully this isn't too confusing, right? So remember, they were asking us specifically about the precipitation of silver chloride, so AgCl, which is, in and of itself another salt, right? So let's pull those two out and look at those two separately. For AgCl, right, we would need the concentration of Ag, and we would need the current concentration of Cl, right? So current concentration of Ag we know is 5 times 10 to the negative 4. Cl is 5 times 10 to the negative 3. And then when those are multiplied together, 5 times 5 gives me 25. When I multiply together exponents, remember, according to MADSBIM, I add them. So that's 10 to the negative 4 plus negative 3, so negative 7. And again, I can move the decimal place back over 1. 2.5 times 10 to the negative 6 moles. Okay, so this is my concentration. The concentration that I have of AgCl, right? So remember, we talked about this earlier, and I've also given it to you again in this problem. The solubility constant for AgCl is 1.7 times 10 to the negative 10, right? So this concentration over here is actually way, way bigger. Way, 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 way bigger than it needs to be, right? In order for us to say that, yes, this will give me a precipitate, right? Remember, this is the absolute maximum amount that can be dissolved in a solution. Well, we have way more than that, so at least some of it is going to precipitate out. So yes, we will get a silver chloride or AgCl precipitate. Whew, okay, so now I think you know just about everything you could possibly want or need to know about solubility products. Thanks for sticking around, and I will see you next time.